Hello everyone, welcome to our webinar on analyzing multibody systems in COMSOL Multiphysics. My name is Arpad Forbergen and I'm an application engineer at Gamax Laboratory Solutions. Today we are going to take a look at COMSOL Multiphysics and how to set up physics for calculating displacements and other structural properties of multibody systems. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. And today's agenda is the following. We start with a brief introduction to COMSOL Multiphysics, some description of the joints, what is available in COMSOL Multiphysics. I will set up a short demo for presenting the capabilities of multibody systems modeling in COMSOL Multiphysics, and at the end I will summarize today's webinar. If you find this webinar a bit fast, don't be worried because we are recording this session, so you will be able to recatch everything and you will see the link in the follow-up email after this webinar. So what is COMSOL Multiphysics? COMSOL Multiphysics is a modeling, simulation and application design environment where all the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today's webinar and the products we are focusing on is a structure mechanics module, multibody dynamics module. That's a trivial solution here, but you can also incorporate with other modules, add-on modules like the rotor dynamics module or to the acoustics module. And also you can take into account the fatigue calculations with COMSOL Multiphysics. And as another solution, you can couple to AC/DC, let's say two permanent magnet motors or other rotating machinery with multibody dynamics simulations. Here you can see some type of joints that are available as conditions in COMSOL Multiphysics. You have prismatic, hinge, cylindrical, whatever. You can have a reduced slot or universal joints. These can be used on attachments or on rigid domains to connect rigid or flexible domains with these joints, and you can apply several boundary conditions and constraints on these joints, but later in COMSOL you will see how to set up these conditions. That's a new boundary type and a new physics property. That's a cam follower connection. So now in COMSOL Multiphysics 5.3a you can set up a cam, whether it's an edge or a boundary, and you can set up a follower that follows that surface or that line. So that's a quite new and interesting new feature in COMSOL Multiphysics. Here are some more examples what you can do with this cam follower boundary condition. It can be a cylindrical cam or a wedge cam or a pin moving in a slot. That's also available with this new type of physics settings here. There's a new option that's so-called lumped mechanical system. That's a pretty new thing in COMSOL Multiphysics, and you can set up like in the AC/DC module an electrical circuit. You can set up the same mechanical model with lumped parameters, and of course you can couple this to any other physics like to a multibody dynamics module, and you can set up suspension system with this lumped mechanical system, and you can connect that to a full multi-body, let's say a car simulation. These are the parameters and ports that can be used in this lumped mechanical system configuration. The well-known components are available, and also as a terminals, it can be a fixed, a displacement node, a velocity node, and so on. There are several options that can be used to fix some or multiple ends. Some examples that can be done in Multibody Dynamics module. It can be a gear train. You can see the velocity field during the rotation, or it can be a bigger multibody system like a helicopter swash plate mechanism. So you can include rigid or flexible blades, and you can take into account the movement of various and several different joints. And you can also apply multibody simulations on home appliances like this washing machine, and you can add other physics like the acoustics module to take into account the generated noise of these rotating domains. And today's demonstration will consider two blocks. One smaller block at the top that will move with a prescribed displacement, and the lower block will be fixed. And due to the friction, we will introduce the heat generation, and we can add the heat transfer in solids physics node. So we will set up a multiphysics example and model here. Okay, so now we are going into COMSOL Multiphysics, and we will set up as a new 3D domain with a multibody dynamics physics interface and heat transfer in solids. So we will use these two modules and physics interfaces to set up our model. And because the upper block is moving, we will use a time-dependent study, but there are other options like an eigenfrequency or eigenvalue solver, or it can be stationary. There are several other options that can be taken into account here. So now we are using a time-dependent model for a multibody dynamics and a heat transfer in solids physics interface. Okay, so from the geometry node, we will set up two blocks that will be 1 centimeter by 5 centimeters by 500 millimeters in an x-axis. That will be the lower block that will be fixed. So we simply duplicate and we set up the block 2, 0.1, and set the corner to 0.2 to 0 and to 1 centimeters. And the same x-axis. Okay, so this is the top block. And because they are moving relative to each other, it's a multi-body module. The geometry node, the last subnode, must be a form assembly. So here, instead of creating a union of the two domains, we need to set up a form and assembly. And yes, we need to create pairs, identity pairs, where the two blocks are connected. And if you build all, and if you go to definitions, this identity boundary pair is automatically generated for you. So the two surfaces, number 4 and number 9, they are automatically created as an identity pair because we need the continuous solution of the temperature field there. Okay, geometry done. Materials, we will add a simple material from the library. So from the built-in section we will select cast iron. Okay, so we go on with the Multibody Dynamics module. So for simplifying the solution we will use rigid domains, but by default all of the included domains are elastic models. But for calculating pretty fast we apply so-called rigid domains for the lower part, and we need to fix since this will not move during our simulation. So right click on rigid domain 1 and we can fix it, or we can add the prescribed displacement, rotation, we can apply force or moment, we can override the mass and the moment of inertia properties, or we can add external masses and we can add the spring foundation. But for simplicity we fix, so it's not moving. Okay, so we do the same for the upper block, rigid domain for the upper block. Okay, and we need to apply a prescribed displacement since we want this little block to move in the x direction with a sine wave. So right click, prescribed displacement in x direction, and let's put a function here with a sine of 10 times t, okay, over 6, and constraint in the y direction that it's 0. Okay, yes, we need to fix the unit, so it's 1/second. Okay, so now it's in meters. It's not moving in the y direction, so in the transverse direction it's not moving. Okay, and we put some force on it, put a minus z direction, a force to push this upper block to the lower one. So apply some force on that block in the minus z direction, let it be minus 100 newtons. Okay, and if we want we can add gravity whatsoever, but that's okay for us, so we apply a force to press together the two blocks. And for the joints section we go to joints and prismatic joint. So we will apply on rigid domain 1 and 2. Now you can see the selection. So these two domains are incorporated into prismatic joint 1. Okay, the centroid is on a boundary level. Let's select this one. So the centroid of this boundary indicates the center of the joint, and the joint is in this x direction. Yes, that's correct, that's the default value here. Okay, and we need to apply to calculate the joint forces using the penalty method. That's okay, because we need that for calculating the friction. And of course, for friction we need to apply some value for that, but you can also add the prescribed motion to the joint, a spring and damper, you can add other additional constraints. But now we are adding some simple friction coefficient to 0.3. Okay, that's all from the Multibody Dynamics node. From heat transfer, quite simple, we need to add the pair boundary heat source to the automatically generated identity boundary pair. And what's generating heat? The heat comes from the other physics from Multibody Dynamics node. And if you click here and just simple click Control Space, you can go to Multibody Dynamics, Prismatic Joints, Prismatic Joint 1, Energy and Power, Energy Dissipation Rate due to friction. Okay, so now we are calling the generated friction, generated heat from the Multibody Physics node, and we are putting this here as a boundary heat source. Okay, and that's all. For simplicity we keep it that simple. To speed up the computation we change to linear elements from quadratic. From the mesh type we add a simple swept. Okay, and because we are using rigid domains there are no displacements, so we can use the same kind of coarse or coarse mesh. Okay, and one thing is missing that we need to solve. It's a time dependent problem. Let's say for simplicity we are solving for 1 second. Let's generate some default plots with get initial value. Okay, so we have the initial values for displacement velocity. These two plots are the default plots for the Multibody Dynamics node, and these two plots, the temperature field and the isothermal contours of the temperature field, these two plots are the default plots for the heat transfer physics. Okay, and just to check this box, the plot the temperature during the calculation. Okay, and let's see how it looks like. Okay, so we will have some nice plots during the solution. So we will see the temperature change as the simulation goes, but I forgot to add some displacement. Sorry here, so we need to add the displacement with a scale of 1. Okay, so now we will have more solutions and much nicer plots here. Okay, so we will see some nice plots during the solution, and I will open up the solved version to see some additional plots there. And then I will go on with some multiphysics options here that you can run. So now you can see, because we apply the sine function, so the upper block is moving, and we have some temperature change as the friction generates heat between the two bodies. Okay, if you need more precision, of course, you can change back to quadratic elements, but for speeding up the computation, I use these linear elements here. So if I open up the solved one, we can see how it looks like. So you can apply more time steps to get a much finer solution, and with just a click you can create a very nice movie on this. So you can see how they move, repeat, and we can see these two blocks moving on top of each other. So this is the temperature field. So that's one kind of solution in the Multibody Dynamics node. There are much more joint types, as you have seen in the previous slides. So that's a very small, brief introduction to the capabilities of this Multibody Dynamics module. And if you want to do more, you can go to true multiphysics. Like on top of heat transfer, you can add, for example, an optimization node on Multibody Dynamics, and you can optimize the position of a pins of a crane link, and it can be used, let's say, to reduce the maximal force, and since we are reducing the force, reducing the maximal stress in the components. And you can add, of course, fatigue calculations, so you can use in any rotating or where you have repeating load, you can calculate and predict the life cycle of such components with the additional module, additional fatigue module. You can also include rotor dynamics, so if you have rotating machinery, you can create Campbell plots and waterfall plots with quite simple and quite easy calculations. And like in this example, if you have gear pairs, you can use this here, this rotor dynamics, to expand the capabilities of this kind of multi-body and multi-physics calculations. You can also include acoustics, as these rotating machines, rotating domains can generate lots of noise. You may want to calculate explicitly what's the sound pressure level and the sound propagation around these objects. So you can also add acoustics module to take into account the radiated sound. As you've seen in my demo example, you can add heat transfer. There are much more examples at the library, and of course you will get the direct links to these models. So due to friction, due to these joints, you can calculate the generated heat. Electromagnetics, and it's in a combination with rotating machines like in motors or generators. You can include bearing calculations, of course, the force is generated inside the bearings, and if you want, you can add an extra acoustics on top of this to calculate the radiated noise. And of course, there are much more solutions for automotive and aerospace, for machinery, robotics, and of course it can be used like for biomechanics applications, for a human body to take into account the comfort and dynamics of a passenger in a car. So these are the capabilities of Multibody Dynamics modules. And to summarize this webinar, we have seen that there are available lots of couplings, so you can create true multiphysics problems with adding a heat transfer or an acoustics problem. You can include shells into these multibody calculations like in a washing machine, so it can be a shell, not primarily a 3D domain. You can include acoustics, whether it's a finite element formulation or a boundary element formulation. You can add this to create a multiphysics model. You can include heat transfer and whatever you can imagine, so you can expand the capabilities of the Multibody Dynamics modules. And there are different types of solvers, so you can solve in a time domain, in a frequency domain, and you can calculate between these domains back and forth quite easily. Okay, and to have some questions, you can reach us at our website, or you can write us directly. So if you want to try out the software, you can do this with the trial version. You have full technical support during this trial period, and as I mentioned earlier, you can have the links for all of the models inside the follow-up email with the displayed slides, and the recorded and edited webinar will be published throughout this follow-up email. So I thank you for your attention and see you in our next webinar in May.